Lecture 2.6, specific heating. Our most important tool for calculating details on thermal processes is the first law. The problem is we can only calculate workings. And when we calculate workings, that really means that we sum areas. But we know nothing about calculating heatings and internal energies. So if we look at the first law, we see that we have work plus heat equals the change in internal energy. This we know because that's just calculating areas. But these two, we know nothing about calculating these guys. To calculate heat, to calculate Q and the change in internal energies, we must understand heat capacities. Maybe I should write that in big letters. Heat capacities, since it plays a central role in ideal gases. To gain intuition on what heat capacity is, we now study the heatings of liquids and solids, not ideal gases. We need to describe how heating changes the thermal properties of matter. So what we're going to see here is that this is a two-part lecture. There's specific heating, Oops, I didn't write specific. This is the type of heating that causes temperature change, and this is where heat capacity lives. And then we're going to compare this to latent heating in the next chapter. And when you look at this, this is no temperature change, but this is a phase transition of the material. So let's go look at that. So now I'm going to start with the thermal properties of matter. So once again, we are not dealing with ideal gases. But liquids and solids. The internal energy now has two terms. It has KEmicro, and now because there's bonds, we have to include PHEmicro. So what we're going to do here is that we want to focus only on the thermal properties of materials. Not the workings. So when I write this, here's my first law. You're going to see here is that I can change either micro or I can change the potential. But no work are we going to look at. So you can see here is that I have KEmicro and I have PHEmicro. So heating changes internal energy two ways. So let's say if I start off right here, here is the heat that's going to go into my system. So here's a flow chart. And from this heat, the thing that I'm going to change here is internal energy. So then I have internal energy. So now there's two ways for me to change internal energy. One path is changing KEmicro. So in this situation, let's say I draw it like this size. Or I could change it this way, where I have PHEmicro. Those are going to be the two ways. So what happens? So in the green box, this is going to be heat and temperature change. This is what we call specific heat capacity. So specific heat capacity lives with heat and temperature change. In the yellow box will be when we change potential energy. So in this case here, we have heat and no temperature change. And this is what we call latent heat. And so we have to deal with both of these situations. So here we go. So let's deal with, in this lecture, we're going to deal only with specific heat capacity and temperature change. So here we go. So we're going to have specific heat capacity. In this chapter, I'm not going to say specific heat capacitor. I'm just heat capacity. I'm going to say heat capacity. There's two types of heat capacity. Right now, because we're dealing with liquids and gases, it's called specific heating. When we get to heat capacity of ideal gases, it's called molar heat capacity. So when you have this, then you have a temperature change. So here we go. If heating a material causes a temperature change, then we know that the change in temperature is proportional to the change in microkinetic energy. This heating is called specific heating. So anytime we've talked about heating up to this point, we only were talking about specific heating when we said heating. And depends on three parameters. Now, I'm going to describe these three parameters intuitively, not really getting into the details of sort of like the mathematics. We'll get to it. So here's the first one. The first one is a material dependent. So there's a material dependence. And what is this? This is what we call, remember, it's called specific heat capacity, but I'm just going to say heat capacity. Heat capacity is the parameter. And the heads up, this heat capacity, it's extremely important. Okay, it plays a big role in this course. So here's what we know. We define the heat capacity by the symbol C. Okay, so that's how we define the heat capacity. So now, what do we know here? So when we say the word heat capacity, we say this: different materials have different capacities for storing, and I'm going to move this over here, for storing internal energy. And I'm going to say that you have a lot of intuition on heat capacity. So if we think about everyday examples, there's a lot of them. But I could think of a couple of examples. The first one is that I'm going to say, when eating a piece of some type of fruit pie, let's say apple pie, you know, that's straight out of the oven. You know very well that if you take the hot pie filling, remains very hot for a long time. So what does that tell us? Well, according to the definition of heat capacity, it stores lots of internal energy. So therefore, it has a high heat capacity value. On the other hand, if you take the pie crust, the pie crust quickly cools in a short time. So what does that says? It stores very little internal energy. So that means here it has a low heat capacity value. You could say the same thing, the other thing that we could say here, we can also say a hot bowl of soup versus toasted bread. If the soup is really hot and you try to put it into your mouth, guess what? You'll probably get blisters. Even though when you had the bread in the toaster and you could see the red hot wires of the toaster, that's at a higher temperature than the pot was. Guess what? You could take that toast and you could eat it right away. So again, the hot bowl of soup has the ability to store a lot of internal energy, so therefore it has a higher heat capacity compared to that of the toast. Now, the second parameter has to do with temperature dependence. What we say here, by the way, I actually forgot something. Let me move back. I should have written this down. What I should have written here is that I should have said this. If I look at the change in internal energy for the pie filling, that is very high. And that means here, it took a more heat, right? In this case, you had more heat to get a bigger change in the internal energy. And what I'm saying here is that this heat capacity of the filling would have to be large. Now, if you look at the toast, the change in internal energy of the toast is not very high. And as a consequence, it has a small heat capacity. So in essence, I could have less heat transferred to the internal energy. I think I want to keep doing this symbolism so that when we actually get to the equation, it's clear. So now let's go with the toast. Here's what we know. Now that we're done with the toast, let's move on. So different materials require different quantities of heating to change its temperature. Okay, so let's think about this. As an example, we have a metal pot filled with water. As we already know, boiling water, let's say to cook pasta, takes a long time. So, in other words, lots of energy transfer has to go into the water to change its temperature. On the other hand, not one, but on the other hand, the metal pot quickly heats up. So very little energy transfer was required to change the metal pot's temperature. So if I look at the heating here, I could imagine that here's the temperature of the water. And then let's say that this is going to be the temperature of the pot. So, and I have to put a lot of heat into the water to get a temperature change. Whereas if I put a little bit of heat into the pot, I can quickly get to the same temperature. And what I'm doing here is that I'm going to assume that these guys are the same temperature change. So we clearly we have to add more heat. Here we have to add less heat. And then finally, the last one is the mass dependence. And so in this case here, we could then say the following thing. Different masses require different amounts of heating to raise its temperature. So let's look at some examples. So here's one. One, if you have boiling water in a cup, and let's say that the cup is 8 ounces, you know what? I don't think I like the way I'm saying this, so I'm going to change it. I don't like what I just said. I'm going to say, if one boils a cup, and let's say this is 8 ounces of water, it requires less heat transfer than boiling a gallon. What's a gallon? It's 128 ounces of water. That's not a surprise. So if I look at the mass of the cup, versus, let's say, the mass of the gallon, this should take very little heating to get to the boiling point, which I'll say is 100 degrees C. Whereas if I need to heat up a gallon, I have to put in a lot of heat transfer. Even though, you know, I said equal sign there, that should have been a proportionality. Even though this temperature change is exactly the same. So in this case, you clearly have less heat required because I have a smaller mass. This guy tells me that it has more heat. Again, that's very intuitive. Now, let's look at the second one here. This is an interesting one. 4th of July, sparklers. Each sparkle or each sparkler gives off a spark whose temperature is 2000 degrees C. That is really hot. Now, I've known if you've used a sparkler, you know that some of these land on your arm. So if a spark lands on your arm, it does not burn. It does not burn you, even though the temperature is 2000 degrees centigrade. And the question is why? Since its mass is so tiny, it contains very little internal energy. And if it contains very little internal energy, that's why it doesn't burn you. Its mass is too tiny. So now we can define what we mean by specific heating. Okay, so here's a good definition. Specific heating causes, oops, that's spelled wrong, causes a temperature change and what do I mean by temperature change? I change KEmicro of a material, where Q specific, which I typically just write Q, is then MC delta T, where M is the mass. Of course, the change in temperature is delta T. And then we define this new fundamental constant or material parameter called the specific heat capacity, or for short, heat capacity. So everything that I just said in some shape or form, you knew intuitively from those examples. So let's go look at this thing here now. For starters here, let's look at some details before we get into interpreting what the heat capacity is. So let's look at the units of heat capacity. So if I solve for the heat capacity, in other words, if I have Q equals to MC delta T, that tells me that if I have the units of heat capacity, it's got to be the units of mass, the units of change in temperature, which is then equal to the units of heating. So I can write this two different ways. I can write this in terms of kilograms, degrees Celsius, or kilograms, Kelvin. Both of these are identical. So just by looking at the units, the heat capacity tells us how much a material has to be heated to change the temperature by 1 degree Celsius or 1 Celsius of a unit mass. So as an example, here's the heat capacity of water, which is one of the most important values in the first exam, which is 4,186 joules per kilogram degrees Celsius. So what that means here is that this is what happens. I have a container, and when I look at this container, I'm going to heat this guy. So this here is water, and then the bottom here is a heat source. So I know this is a heat source, and I know that heat is going to transfer into this water. Let me copy this. Oh, I want to copy, and I'm going to just put it right over here. So what I know here is that, let's say that this water starts at room temperature, which is 20 degrees C, and you could see that this is temperature 1. So this guy is heating. Now, what I'm going to do here is that I'm going to transfer how much heat. So if I transfer 4,186 joules of heat transfer, this thing raises its temperature by 2. By the way, one thing that I neglected to say here is that the mass of the water is 1 kilogram. So then what happens here is that the temperature has changed by 1 degree Celsius. That's what that thing is telling me. So now we start the process of interpreting heat capacity. So let's do that. So to get the idea of heat capacity, well, I'm going to start with an analogy. Okay. And the analogy that I'm going to use here is what is the meaning of inertial mass. I know a lot of times people call it inertia, but it's really inertial mass. Okay, so what happens here is that you most likely learn that the role of mass in Newton's second law is that it's a scaling factor. So what do I mean? A scaling factor. So from Newton's second law, and the acronym that's very commonly used is N2L, what it says here is that the acceleration is equal to the net force divided by the mass. And you can see here is that this is directly proportional to the mass. So what does that mean picture-wise? So picture-wise, I could imagine that I have a block. Okay, here's this block right here. And then I have this block right here. So if I look at this block, let's say that this is that mass, and then this other block over here is like this. So I'm going to imagine that this is a tiny mass, and this is a much larger mass. So what we're going to do here is that we're going to apply the exact same force on each block. So that means we have this amount of net force acting on this, and the exact same net force here. What actually happens here? So what happens here is that as this block reaches here, or it accelerates away, here's what we see. What we see here is that this acceleration is large because it's proportional to the smaller mass. This acceleration is small because it's proportional to a larger mass. So what we're seeing here is that if I have a smaller mass, that implies that I have less resistance to change motion. And then if I have a larger mass, then I have more resistance to change in motion. And a lot of times people say that it's this, that this is the law of inertia, that it's the first law of Newton's law, not Newton's second law. If you look at Newton's first law, note that there's no mention of mass. There is mention of an inertial frame of reference, but this isn't the mechanics course, so we're not going to go there. So how is inertial mass defined? Is inertial mass defined? By the slope of A versus F net. That is the way mass is defined. So if I look at this thing, I imagine that I have the following curve. So here's my coordinate system. And I'm going to be plotting A versus F. So if I look at Newton's second law, it tells me that the acceleration is equal to 1 over the mass times the net force. And this is the correct way to write it. Why? Because this is the cause and this is the action. So then this immediately tells us that when I define the slope, it's defined as 1 over mass like this. Now note that there are other ways that people talk about the meaning of mass, like about how much stuff is inside, but this is the definition of mass. So you can see here that this is a steep slope, or I could have something that has a less steep slope. And here's where we define what we just said. So what we said here is that if I have a less steep slope, then that tells me here is that I have a larger mass in the denominator. So therefore, it tells us that it's harder to accelerate, which means it has a larger mass. So now I'm putting in there by hand. You know, I should have not put I should put this sign in here. Now, if I have a steep slope, then this tells me that I have a little tiny mass. So this means here is that this is going to be easier to accelerate. So therefore, it has a smaller mass. This is where the phrase, right? This is where the phrase that this has more resistance to changes in motion. And this is where people would say that this object has a lot of inertia. This guy right here tells us that there's less resistance to change. Now what I want to do here is that I want to take this idea and I want to apply it to specific heating. So I want to apply these ideas to specific heating. So let's look at what specific heating tells us here. So specific heating tells me that this is MC delta T. Or I can rewrite this. I can rewrite this as, again, this is the cause here. This is the cause, and this here is the action. So if I change that, it should look MC over 1 times the heat. That immediately tells us that the slope of this guy is then going to be what? It's going to be 1 over MC, where MC is known as the thermal mass. So you can see that there is a lot of similarities in this thing here. So we could then say that the role of thermal mass you know what? I should say thermal. Is similar to that of inertial mass in Newton's second law. Okay, to make my argument very clear that I want to focus on heat capacity, assume the mass never changes. So, of course, that means that this guy has to be a constant. So let's plot this thing now. Okay, so when I go and I plot this thing, let's go look at this guy. So I'm going to be plotting temperature versus heating. So if I have a less steep slope, let's say here, we could say here is that this is less steep. What does that mean? This tells me that I have a small temperature change. The only way I can have a small temperature change if the heat capacity is large times Q here. So in other words, this tells me here that I have a large thermal mass. And really, I'm saying a large heat capacity. On the other hand, if I have something that goes like this here, this is a very steep curve. So if I follow this out here, you can see here is that this change has a small heat capacity. So as a consequence, I can have a big, oops, not what I wanted, temperature change. So this tells me that I have a small thermal mass. So if I summarize it like we just did earlier here, we could then say, so if I have a less steep slope, oh, that's not right. Let me change that. Then that tells me that I have to, so if I look at this thing from our slope equation, we then see that this is going to have some mass, but then it's going to have a large heat capacity. And that tells me that I'm going to have higher heat capacity, which then means it's easier to change temperature. I'm going to move this over. So now if I have a curve that says that it's I have a steep slope, then I have a smaller heat capacity. So then we say that this is a lower heat capacity, which means, you know what? I said easier here. It should have been harder. Here, it should be easier to change temperature. So what do we say? This has more resistance to change in temperature. This has less resistance to change in temperature. So now, here's what we should start to look at here. What I want to show you here is that now I want to come in and I want to look at, I want to interpret heat capacity values. And what I'm going to do here is that I'm going to use PhET, and I'm going to use the applet states of matter, which is provided in the link. And so the first thing that I want to show you here is that I want to show you this table. So I have a table here, and the way I want you to look at this thing here is that I want you to see here is that these guys are metals. These guys right here are liquids. So just by looking at that, you could see that the metals have much smaller heat capacity values compared to the liquids. So here we go. Metals have smaller heat capacities or heat capacity values. This means that their temperatures can change quickly. For example, place a metal rod in a fire, and one feels the heat or feels the hotness almost immediately. So physics-wise, Q changes the internal energy implies how many ways can this heat transfer be stored as internal energy. That's really the details of this here. And so here's the answer. Metals are good electrical conductors. Because it's easy to move electrons. And therefore, they have less resistance. So, in fact, electrons in metals act more like ideal gas particles. And the question, of course, is why again? Electrons only move translationally. As drift velocities. And they don't collide with other electrons. They collide with the ions in the metal. So now, if I go look at this applet, what you're seeing here, what's going on? There you go. You could see here that if I have an ideal gas, they can only move linearly like this, translationally. There's nothing special about them. So if I come back to my screen here, what I can then show you here is that I just was getting an image of this guy. So if you look at the image of this, you're seeing that if we're talking about translational, motion, they're moving effectively in one direction. So we then say that KEmicro can only go into K translational, which is then proportional to the temperature. So all of the heating goes into K translational, nothing else. So then what we could say then is that when heating metals, all the heat goes directly into K translational, where temperature changes quickly. Now, that's pretty hard to understand that right now. And the way you're going to get the idea here is that now let's look at the next thing. Look at the liquids. By a factor of 10 or more, they're bigger than the liquids. I mean, than the metals. In order to really understand this, we got to get to these guys here. And what we know here is that liquids have larger heat capacity. And of course, the question is, why do they have larger heat capacities? Liquid molecules like water have more ways to store internal energy. And what I mean by that is, let's go back to the applet. Okay. So I'm going to go back to the applet. And then I come right here. So this is what the ideal one is. But now look at water. If you look at water, what you're seeing here is that, note that there are different rotations. Now note, this is a gas. This is not a metal. But if I look at the liquids, you could see how there's a lot of motion that's going on, where all of these little guys are oscillating and vibrating and everything like this here. So I just took an image of this thing, and let me show you what we're seeing here. So now, if I go back to my screen here, you're seeing here is that you just witnessed that these guys are doing what? They're rotating. They're spinning. And believe it or not, depending on the temperature, they might even be oscillating. So now when I look at the heating here, let's look at the heating. So when I look at the heating, these guys have micropotential energy, and microkinetic energy. But because of their motions, it's more complicated now. For example, there's K translational. There's K rotational. And there's K vibrational in water. So what I'm saying here is that you could imagine that I have water molecule. Oops, I did not put it here. Here's my water molecule. Now I got to attach my hydrogens. So it's looking something like that. So when I look at this thing, translational means it moves at mv/rms squared. But now there's two possible rotations. It could rotate like this, or it could rotate like that. So then I have, turns out to be, two rotational kinetic energies. Now, if you look at a spring system, this guy could now oscillate. And this, now I realize that that's not a really good picture of what I'm trying to show you. But let me extend these guys. The bonding between the hydrogen and the oxygen is sort of like spring-like. And it turns out that in this situation, you have kinetic energy in the spring. And it turns out that I can write, on average, the kinetic energy can equal to the spring potential energy. But either way, you see that there are more ways to actually do this. So when heating liquids, the heating is distributed among the different kinds of motion. And K translational, which is proportional to temperature, gets less energy transfer. Therefore, liquids are harder to change their temperatures. This is what the heat capacity tells you. How many ways is the heat transfer stored in the material's internal energy? Right? That's what we're really asking. And so here's what we find. So if I look at the, let's say, the metals, the heat capacity of metals, well, that's proportional to the change in internal energy. And in metals, because they act like ideal gases, you look at the translational change, and what you're seeing here is that because you deposit all of the energy into the translational, it changes temperature quickly. On the other hand, the heat capacity of liquids is proportional to the internal energy, but this here is proportional to not only the translational plus the rotational plus the vibrational. So it's spreading out the energy in more places than one. So this tells us that it changes temperature much slower. So what I want to do here is that I want to end this thing I want to talk about the misconception of heat capacity of space shuttle tiles. And this video is about 1.5 minutes. And the question that I want you to answer for me, do the tiles have a high or low heat capacity? Okay. So what I'll do here is that I'm going to go and let's watch the whole video. And I want you to pay close attention to what is being said. Now note, you could find this link in the lecture 2 links. Okay, so I'm going to go back to the web, and I have a video right here. So here I go. So let's look at this, listen to this guy.
We have the raw 9-pound material that we use. Now these have been in there at 2200 degrees for an hour. So you'll see they're blazing hot. Now most things, if you put in an oven like a fluid heat in, it would disintegrate after a couple of minutes. But these things have been in there hours. If you put it in metal, it may, if the metal did not melt, at least it would conduct the heat and keep the heat for so long that you couldn't get near it, well, within hours. Well, look at that. I mean, you can take this off. It dissipates the heat so quickly that you can actually pick these up while they're glowing, molten in the middle. Well, they were in the oven at 2200 degrees. So you can go ahead, you can pick them up and take a picture. Just make sure you don't pick it up on the edges, just at the corners. Just at the corners. I mean, I just don't want to get anybody. Yeah, there you go. That's perfect technique right there. Now you'll feel the warmth, which is you can touch it. I mean, imagine at 2200 degrees, get down. Yeah. And the difference with the densities is you'll see these lower densities. You'll see how they can dissipate the heat. Well, look at that. That's the 22 pound per cubic foot. It's going to glow for hours. You could come back after dinner and roast marshmallows on that. But these emit the heat really rapidly. I mean, a good example of how this works is that when the shuttle comes in, it gets up to about 2500 degrees. But yet, the surface is going to be.
This is
So let's go look at this thing here. So he said something not correct. So here's what they said here. He says that as soon as they are pulled out of the oven, right? As soon as they are pulled out of the oven, and it turns out to be because this is in the United States, he didn't say whether it was Celsius or Fahrenheit. By the way, he said 2200, so I should write 2200. He means Fahrenheit, and Fahrenheit is about 1200 degrees C. Okay, he says the speaker is able to pick them up immediately. By the edges. That's important, as you'll see. And note what he also says. And here's what he says here. He says, maybe I should put it here, it dissipates heat very quickly. So if it dissipates heat quickly, then this immediately implies that it has a super low heat capacity. Unfortunately, he's not correct. This is not correct. And the reason why it's not correct is that there's a couple of reasons. Okay, this is not correct for these reasons here. Don't you remember he says that the speaker stated stated it takes hours to heat up. If it takes hours to heat up, this immediately tells you that it has a large heat capacity. And note, he also says, do not touch the faces because they are very hot. And in this case, they'd be essentially 2200 degrees Fahrenheit. So this immediately tells you that this guy here, that these tiles, so the tiles store a lot of internal energy. Yeah, they store a lot of internal energy for a long time. Okay, they change temperature over very slowly over a long time. So the heat capacity of shuttle tiles is very large. So I guess the question that I should answer here is that why can they pick it up immediately? And I think the way to answer this question here is that I want to use an analogy. And this was my wife cutting my son's hair. And so what you found here is that we put a metal chair out, and he had no t-shirt on, and he sits in the metal chair, and he immediately says, the chair is too cold. So we had a second chair. And in this case, we had a wooden chair. And then when he sits in the wooden chair, he says, it's much warmer. And I tried to tell my wife and him, I goes like, he's not correct. And the reason why he's not correct both of these chairs are at room temperature. The metal chair is not colder than the wooden chair. It's not the temperature that's important here. It's a concept that we haven't talked about. It's the thermal conductivities. So it's not the temperature, it's the thermal conductivity. So if you had a metal chair, what you'll find here is that it has a high conductivity constant, thermal conductivity constant. So what it does here is it transfers heat out of my sun quicker. Whereas if you had the wooden chair, it has a low conductivity constant, and so it transfers heat out of my sun much slower. So he thinks that it's warmer, but they're the same temperature. Tiles are primarily made out of silica, which has a very low heat conductivity. So tiles have a low thermal conductivity. Which implies that it transfers heat very slowly. So it doesn't, so the important thing of this here, this implies it doesn't overheat the inside of the shuttle as it re-enters the atmosphere. And according to him, the shuttle gets to be about 2,500 degrees C as it's re-entering the atmosphere. So now, to answer the question, why hold them by the edges? Why are the edges so much cooler than the center? The quick answer is less surface area which then means less heat transfer. In other words, the corners and edges cool quickly because they're surrounded by the cold air of the room. When I say the cold air of the room, relative to the cube, due to the low conductivity of the material, the corners are effectively isolated from the rest of the cube. It's just not good at transferring energy, just like the wooden chair wasn't good at transferring energy, where the metal chair was.